Hello everyone, my name is Matthew Chin and I am presenting the composite design pattern. So the intent of the composite design pattern is to compose objects into tree structures to represent part-whole hierarchies. This allows the client to treat groups, also known as composite, and individuals, also known as leaves, uniformly or in the same way. So if we look to the example on the right, we see that we can imagine that we have two types of objects, products and boxes. A box can contain several products as well as a number of smaller boxes. And these little boxes can also hold some products or even smaller boxes and so on and so forth. So if we see these boxes highlighted in blue and we see these items highlighted in orange or leaves, how would we determine the total price of this order? Well, one way we can do it, which is not as efficient as you would like, is to try a more direct approach, which involves unwrapping all the boxes and going over all the products and then calculating the total. That would be doable in the real world, but in a program, it's not as simple as just running a loop. You have to know the classes of products and boxes you're going through, and the nesting level of all the boxes, and other nasty details beforehand, which makes the direct approach more difficult and even impossible. So, what's the solution? How do we find this total price? Well, for a product, it'd simply return the product's price, and for a box, it'd go over each item the box contains, so its children, and ask for its price, and then return a total for this box. As an example, if one of these items were even a smaller box, that box would also start going over its contents, and so on, until the prices of all the inner components were calculated, which means all the prices, it went through, which essentially means it went through the whole tree. We reached all the leaves and we returned all the prices of those leaves. And the greatest benefit of this approach, why is this approach better than the direct approach? Well, it's because you don't need to care about the concrete cases of the objects that compose the tree. You don't need to know whether an object is a simple product or a sophisticated box, because we treat them all with a common interface and we treat them all the same, because their operations are so similar. So, as this example shows, he asks for the price and he's a composite. Let's say he's also a composite and he says, "Hold on, please." And now he goes to all his children, which are the little guys behind the door, and he asks for their price and returns it to the box that asks, "What's your price?" So when do we actually use a composite? Well, we use it to show part-whole hierarchies of objects, as we stated in the last slide. We also use it when we need to treat all objects the same way or uniformly. And we also construct data representation of trees, which makes the data more organized and clear. And we also use it when we want our clients to ignore the difference between composition of objects and individual objects, essentially meaning the same thing. We're treating them the same way. We can see this in a file system. If we have a folder and other files, we have very similar operations, which would be an open operation. Let's say, for example, an open operation on a file would just open the file and show the contents inside, and an open operation for a folder would work the same way, where we'd open the folder and reveal its contents, which could be subfolders and files themselves. So what is our motivation? Why are we using this? Well, when using many similar objects, we use composition to avoid using each object differently. So if we want to make recursive calls, it would be a lot easier, and it will call all the leaves of the objects. And we'll see an example with an open all call on the object root, which can open all the folders and files, allowing for the full project to be opened in a single call. Something like opening a project on VS Code or Eclipse works exactly the same. This is a UML diagram for the composite design pattern. It shows all the participants in the diagram, including composites, clients, the leaf, and the component itself. Now, one thing to note here is a leaf and a composite, they are both a component. And the client interface, which we'll see on the next slide, it allows them to manipulate objects in composition through the composite interface. And we'll talk more about that later when we see actual code. For the component, it declares the interface for object composition and implements default behavior, which we'll see later on. It also declares an interface for accessing and managing the child components. Another thing is the component interface describes operations that are common to both simple and complex elements of the tree. Now, what is a composite? A composite, or a container, is an element that has sub-elements, leaves or other containers. A container doesn't know the concrete classes of its children, and it works with all sub-elements only via the component interface. So, a container can delegate the work to its sub-elements, processes intermediate results, and then returns the final result back to the client. As we talked about, it goes through all its children, and it returns the price back to the client. It also defines the behavior for components having children. It stores its child components, which we'll see, and implements child-related operations to the component interface, whether it's through its default methods or other operations. A leaf is a basic element of a tree, and of course it doesn't have children or sub-elements. Usually the leaf components end up doing most of the real work since they don't have anyone to delegate the work to, unlike composites. And a client we talked about already. The client works with all elements through the component interface, and as a result, the client can work in the same way with both simple or complex elements of the tree. So here is an example of some structural code, and this is a component. And remember, a component could be a leaf or a composite. And the implementation will be the same for both the composite and the leaf for the component. So, like we talked about in the last slide, we have a default method, or a public string default method, which all these methods will be implemented throughout the leaf and the composite implementations. So, a public array list of components called getChildren is one of the methods, and that'll just return all the children. Note that, of course, leaves don't have children, so we will see how to implement all of these last three operations in the the leaf implementation. So, public boolean add component will just return true if component C was successfully added to the components list. Now, public boolean remove component will return true if component C removes the component successfully from the components list, which we will see what the component list is on the next slide. So, of course, to implement the composite class, we have class composite implements component, because a composite is a component. And we'll have two private variables, being an ID, which is a string, and an array list of component called components. And public composite string identification, that is your constructor, and it will initialize your private variable ID to identification, whatever is entered. Now here's where things get a little more complex, being with the default method. The default method will return the ID of the object itself, as well as if it is a composite, which we know it is, then it will go through all the children using for component child get children, and we will return a ID for them. So how that works is we are going to navigate through each of the children, and we're going to get its children, and we're going to call default method on those, which will also, if they have another smaller box or smaller composite, it will access its children as well and return it. So we're basically navigating or kind of recursing through the whole tree, or traversing the whole tree and returning all the IDs. The operation getChildren itself will return the components, which would be the array list of its children. And if we want to add a component, C, we will return components.addC, which will return true if it was successfully added. Same thing for remove component, will return true if component C is added or removed from the components array list. Now for the leaf, it's a little different because we don't actually have children here. So we just need one private here, which would be the ID itself. So with the constructor, the same thing. We have a string identification, which initializes to ID. And for the default method, because we know we don't have any children, all we have to do is return ID. And also the same thing applies for getChildren. We don't have any children, so we will return null and return false for both the add component and remove component, because we don't have any children. So in summary, the composite pattern provides a structure to hold both the individual objects and composites. The composite pattern allows clients to treat composites and individual objects uniformly or the same way. And a component is any object in a composite structure. Components may be other composites or leaf nodes. And that's it. Sources are refactoring.guru, where I got the cool diagrams, Geeks for Geeks for implementation and learning about it, also with the how to do in Java. Thank you for watching.